Something is wrong with reality. Particles change behavior when you look at them. Galaxies move at speeds that break the laws of physics. The universe is expanding at two different rates at the same time, and no one knows why. You're about to see the experiments scientists wish they could undo, the numbers that refuse to add up, and the cracks forming in everything we thought was real. If this fascinates you, hit subscribe and stay with us. What's coming next gets stranger with every chapter. Prepare yourself. We begin. A single particle is fired at a wall with two slits. Nothing else. No trick, no hidden machinery. And yet, what happens next has forced physicists to question whether reality exists when no one is looking. The setup sounds simple. Scientists shoot tiny particles, like electrons, one at a time toward a barrier with two narrow openings. Behind that barrier sits a screen that records where each particle lands. Common sense says each electron must pass through one slit or the other. After thousands of shots, you should see two stripes on the screen, matching the two slits. That is not what happens. Instead, the screen shows many stripes, a pattern of light and dark bands. This is called an interference pattern, and it only appears when something behaves like a wave, not a solid object. Imagine dropping two pebbles into a pond at the same time. The ripples spread outward, crash into each other, and create a striped pattern of overlapping waves. The electrons on the screen looked exactly like that. One particle, going through two slits at once, interfering with itself. Scientists thought this had to be a mistake. So they placed a tiny detector at the slits to watch which one each electron actually went through. The pattern vanished. The moment the electrons were observed, they stopped behaving like waves. They became ordinary particles again, passing through one slit or the other, and the screen showed two simple stripes. Turn the detector off, and the strange wave pattern came back. Read that again. The act of watching changed the outcome. This is not philosophy. This is a real experiment, repeated thousands of times in labs around the world, with electrons, photons, atoms, and even small molecules made of hundreds of atoms. The result never changes. Unobserved matter behaves like spread out possibility. Observed matter behaves like a solid thing. The question no one can answer is what observation actually means. The detector does not need to be conscious. It does not need a human looking at it. The simple act of recording information about the particle is enough to collapse the wave into a single point. Somehow, the universe seems to know when it is being measured. Physicists call this the measurement problem, and it has tortured the field for nearly 100 years. Some argue that reality only takes a fixed shape when interaction occurs. Others suggest that every possibility actually happens, and observation only reveals which version of reality we ended up in. A few go further and say consciousness itself plays a role in creating the world we see. Whatever the answer, the implication is staggering. The solid world around you, the chair, the wall, the screen you are looking at, may not be solid at all when no one is paying attention. It may exist as a haze of probability that only sharpens into reality when something checks. If that is true, then the entire universe could be running on a rule we never noticed. A rule that says nothing is fully real until it is forced to be. And this is the simplest of the experiments scientists have done. Because if a single particle can sense being watched, then two particles separated by the entire width of a galaxy can do something even more impossible. In a laboratory, scientists split a single particle of light into two. They send one of them across the room. They send the other one through a fiber optic cable to a station miles away. The two particles never touch again. They are completely separated. Then a scientist measures the first one. In the exact same instant, the second particle reacts. Not a millisecond later, not a microsecond later. The same instant, as if the two particles were still the same object, ignoring all the space between them. This is called quantum entanglement, and Albert Einstein hated it. He called it spooky action at a distance, and spent the last decades of his life trying to prove it could not be real. He lost that fight. Here is what is happening, in plain terms. When two particles are created together in certain ways, they become linked. Whatever property you measure on one, its spin, its direction, its tilt, instantly determines the matching property of the other, no matter how far apart they are. You could place one particle on Earth and the other on the far side of the galaxy. The result would be the same. Touch one, and the other answers. This breaks something fundamental. Einstein proved that nothing in the universe can travel faster than light. A beam of light from the sun takes about 8 minutes to reach Earth. The closest star outside our solar system is over 4 light years away. Information should be locked behind that speed limit. But entangled particles do not seem to send a signal at all. They simply act as if the distance between them does not exist. As if they are still touching across the void. For years, physicists believed there had to be a hidden explanation. Maybe the particles secretly agreed on their answers before being separated, like two coins flipped together and then sent in opposite envelopes. Open one, you instantly know the other. In 1964, a physicist named John Bell designed a test to settle the question. He worked out a mathematical limit. If the particles were secretly carrying hidden instructions, the test results could only go so high. If they were truly linked across space, the results would shatter that limit. When the experiment was finally run, the limit broke. It has been broken every time since, in laboratories around the world, with better and better equipment. In 2022, 3 scientists won the Nobel Prize for proving that hidden instructions cannot explain what is happening. Reality really does work this way. 2 objects, separated by any distance, behaving as one. Scientists are now using this effect to build unhackable communication networks and computers that solve problems no normal machine ever could. Engineers have already sent entangled particles between satellites in orbit and ground stations on Earth, proving the connection holds even from space. What no one can explain is why. Some physicists believe entanglement means space itself is a kind of illusion, and that everything in the universe is connected at a deeper level we cannot see. Others believe the particles are still touching through a dimension we have no access to. Whatever the truth, the universe is openly admitting that distance does not always matter. 2 particles can ignore the entire cosmos between them. And this is only the second strange thing. The third is so disturbing it suggests the universe itself is breaking. 2 teams of scientists. 2 of the most precise measurements ever taken. One simple question: how fast is the universe expanding? They got 2 different answers. Not slightly different. Not within a margin of error. Completely, mathematically, impossibly different. And after years of double-checking, triple-checking, and rebuilding their equipment from scratch, both teams arrived at the same conclusion. They were both right. Something is wrong with the universe. The story starts about 100 years ago, when scientists discovered that galaxies are flying away from each other in every direction. The universe is not still. It is growing. Everything is getting farther apart, like raisins in a loaf of bread rising in the oven. The speed of that expansion is one of the most important numbers in all of science. It tells us how old the universe is, how big it is, and what its final fate will be. There are 2 main ways to measure it. The first method looks at light left over from the very beginning of the universe. Almost 14 billion years ago, the cosmos was a hot, glowing soup. As it cooled and stretched, it released a faint glow that still bathes the sky today. By measuring tiny patterns in this ancient light, scientists can calculate exactly how fast space has been stretching ever since. This gives one answer. The second method looks at the universe as it is now. Astronomers find special stars and exploding stars whose true brightness they know exactly. By comparing how bright these objects should be to how bright they actually look from Earth, they can measure distances across the cosmos. Watching how those distances grow gives a second answer. The 2 answers do not match. The early universe method says space is expanding at one speed. The modern universe method says it is expanding noticeably faster. The gap between the two is small in everyday terms, but enormous in physics. It should not be there. According to every theory of how the universe works, both methods should produce the exact same number. Scientists call this the Hubble tension, and it is currently one of the biggest crises in physics. For years, researchers assumed someone had made a mistake. Maybe a telescope was miscalibrated, maybe a calculation was off. But teams around the world have now used different instruments, different stars, and different techniques. The new James Webb Space Telescope, the most powerful eye humanity has ever built, has confirmed the modern measurement. The gap will not go away. This means one of two things. Either our entire model of the universe has a missing piece, a force, a particle, or a kind of energy we have never detected, or space itself is doing something we do not yet understand. Some theorists think a strange form of energy may have suddenly switched on early in cosmic history. Others believe there may be an unknown particle reshaping how the universe grows. A few suspect the laws of physics themselves may not be the same in every region of space. Whatever the truth is, the universe is keeping a secret. It is expanding faster than it should be, and our best science cannot account for it. And the missing piece may be hiding in something far stranger. Something that makes up most of everything around us, and yet has never been seen by human eyes. Look up at the night sky. Every star, every planet, every gas cloud, every speck of light your eyes can detect adds up to only about 5% of what is really out there. The other 95% is invisible. Most of it is something scientists have named dark matter, and after nearly a century of searching, no one has ever directly seen it, touched it, or trapped a single piece of it. It does not glow. It does not block light. It passes through ordinary matter like a ghost, and yet it is everywhere. The first clue came in the 1930s, when a Swiss astronomer named Fritz Zwicky noticed something impossible. He was studying a giant cluster of galaxies moving through space. By the rules of gravity, the galaxies were flying around far too fast. They should have torn themselves apart and scattered into empty space billions of years ago. Something was holding them together. Something with enormous gravity. Something he could not see. He called it dark matter, almost as a joke. The name stuck. Decades later, an American astronomer named Vera Rubin found the same problem inside individual galaxies. She measured how stars move around the center of their galaxy, expecting the outer stars to move slowly, the way distant planets in our solar system move slower than the inner ones. Instead, the outer stars were racing along at speeds that made no sense. Without extra gravity from somewhere, those galaxies should be flinging stars into the void like water off a spinning wheel. But they were not. Something invisible was wrapped around every galaxy like a giant ghostly halo, gripping the stars in place. Today, the evidence is overwhelming. Scientists have measured the way light bends around galaxy clusters, and the bending is far too strong to come from visible matter alone. They have mapped the cosmic glow left over from the early universe, and the patterns in that glow can only be explained if some invisible substance was already shaping the cosmos when it was young. They have even watched two galaxy clusters collide and seen the dark matter clouds pass right through each other while the visible gas crashed and slowed down. The conclusion is hard to escape. Dark matter exists. It outweighs everything visible by roughly 5-1. The shape of every galaxy, including our own Milky Way, depends on it. Without it, galaxies would not have formed in the first place. Earth, the sun, and you would not be here. And yet, no one knows what it is. Scientists have built enormous detectors deep underground, shielded from cosmic noise, hoping to catch a single dark matter particle as it passes through. Some experiments use giant tanks of liquid xenon. Others use crystals chilled to near absolute zero. After decades of waiting, the detectors have caught nothing. The leading theories keep getting ruled out. Each new failure narrows the search and deepens the mystery. This means that everything you have ever seen, every star, every world, every living thing, is only a thin layer of foam on top of a hidden ocean. An ocean we cannot detect, cannot describe, and cannot escape. And dark matter is only the beginning, because something else, something even stranger, is pushing the entire cosmos apart. For most of human history, scientists believed the universe was either standing still or slowly slowing down. Gravity, they thought, would eventually win. Every galaxy, every star, every atom would be pulled back together. The expansion of space would lose its push, like a ball thrown upward losing speed before it falls. In 1998, 2 teams of astronomers proved the opposite. The universe is not slowing down, it is speeding up. And whatever is doing it has so much power that gravity itself is being overruled across the entire cosmos. This was not what anyone expected. The 2 teams were working separately, measuring the brightness of exploding stars in distant galaxies. These exploding stars, called supernovae, always shine with about the same true brightness, which means they can be used as cosmic mile markers. The dimmer they look, the farther away they are. When the scientists compared their measurements, something did not add up. The distant supernovae were too dim. They were farther away than they should be. The only explanation was that space itself had been stretching faster and faster for billions of years. Galaxies were being pulled apart by some invisible force, growing more distant from each other with every passing second. The discovery was so shocking that the scientists checked it dozens of times before publishing. Then they won the Nobel Prize. The mystery force was given a placeholder name, dark energy. Not because anyone knew what it was, but because nobody had a better word for it. The dark simply means hidden. The energy means whatever it is, it carries power. Here is the most disturbing part. Dark energy is everywhere. It fills empty space. The more space there is, the more dark energy there is. As the universe grows, it generates even more of the stuff that makes it grow faster. The expansion feeds itself, and dark energy is winning. It now makes up almost 70% of everything in the universe. Combine it with the invisible dark matter we cannot see, and ordinary matter, the stuff of stars, planets, people, is left as a small leftover. The cosmos is mostly made of things we have never identified. Scientists have searched for decades for what dark energy actually is. One idea is that it comes from empty space itself, that the vacuum is not really empty but humming with a faint repulsive pressure. When physicists try to calculate how strong that pressure should be, they get a number that is wildly off, sometimes by a factor so massive it is considered the worst prediction in the history of science. Another idea is that dark energy is a kind of field flowing through the cosmos, slowly changing over billions of years. Recent measurements from a giant survey of galaxies have hinted that this might be true. Dark energy may be weakening over time. If it is, the universe could be entering a new phase no one predicted. The stakes are enormous. If dark energy keeps growing stronger, the universe will eventually rip itself apart. Galaxies will fly out of view, stars will be pulled away from their planets, atoms themselves may unravel. Scientists call this possible ending the Big Rip. If dark energy weakens or reverses, the cosmos could collapse instead. Either way, the fate of everything depends on a force we have never seen. And the strangeness is not only in what fills space, some of it is written into the oldest light in the universe. If you could see the universe as it was when it first cooled down, almost 14 billion years ago, you would see a glowing fog stretching in every direction. That fog is still there. It is the oldest light in existence, a faint hum of energy left over from the birth of the cosmos. Scientists call it the cosmic microwave background, and it bathes the entire sky. For decades, telescopes have mapped this ancient glow with incredible precision. The result looks like a speckled, patchy sphere. Tiny temperature differences, smaller than 100,000th of a degree, mark where matter once clumped together to form the first galaxies. The pattern matches theory almost perfectly. Almost. Buried in that map, in the direction of the constellation Eridanus, sits a region that has no business being there. It is colder than the rest, much colder, and it is enormous, about 1.5 billion light years across. Scientists call it the cold spot. To understand how strange this is, picture the universe as a giant pool of water with very gentle ripples on its surface. Every ripple is small. The whole surface should look smooth, with only tiny variations from one place to another. Now, imagine a single crater, scooped out of the water, far deeper than any other ripple, large enough to swallow countless galaxies. That is what the cold spot looks like. Standard cosmology cannot explain it. The early universe was supposed to be uniform, with small random fluctuations sprinkled evenly across the sky. A feature this huge and this cold has roughly a 1 in 500 chance of forming naturally. Worse, follow-up measurements with newer satellites and telescopes have confirmed it. The cold spot is real, and it is not going away. So what is it? One theory is that the cold spot marks the location of a giant cosmic void, a region of space that is almost completely empty of galaxies. When light from the early universe traveled through that void on its way to us, the void's missing gravity could have stretched the light slightly, draining a small amount of its energy. That would make the region appear colder on our maps. Astronomers have searched the area, and they have indeed found a hint of a vast emptiness called the Eridanus supervoid. The problem is, even that supervoid does not seem big enough to explain the size of the cold spot. The numbers do not quite work. So researchers began considering wilder ideas. The most extreme of them is that the cold spot is a scar, a bruise, evidence that our universe once collided, long ago, with another universe. In some versions of physics, our cosmos is one of many, each bubble of reality floating in a larger landscape. If two of those bubbles ever touched, the contact could have left a permanent mark, frozen into the early light of our universe. The cold spot, according to this theory, may be the imprint of that ancient collision. Other universes, brushing against our own, leaving a fingerprint on the sky. No one can prove it. No one can disprove it either. The cold spot remains one of the most quietly disturbing things in modern astronomy. A pothole in the universe with no satisfying cause. And it gets worse, because the same map of ancient light hides something even more uncomfortable. A pattern that seems to point straight at us. The universe is not supposed to care about you. Every map of the cosmos, every theory of how it formed, agrees on one thing. The universe has no center, no preferred direction, no special place. Galaxies are scattered across space in a roughly even pattern. Whatever direction you point a telescope, the sky should look statistically the same. That belief has held for 100 years. Then, in the early 2000s, scientists started looking very carefully at the oldest light in the universe, the same ancient glow that revealed the cold spot. They were searching for patterns in the tiny temperature differences across the sky. What they found made them go quiet. The largest patterns in the cosmic glow appear to line up with something. Specifically, with the plane of our solar system and with the equator of the Milky Way. The biggest hot and cold regions of the early universe seem to form an invisible axis. An axis that points almost exactly along the same line as the orbits of Earth, Mars, and the other planets around the Sun. This should be impossible. Our solar system is a few billion years old. The pattern in the ancient light is almost 14 billion years old. The two have nothing to do with each other. There is no known reason why the largest features of the entire cosmos should care which direction our tiny planet orbits. And yet, the alignment is there. Statistically, it is unlikely enough to make physicists deeply uncomfortable. One astrophysicist gave the pattern a half-joking nickname, and it stuck. They call it the axis of evil. Several things could explain it. One is pure coincidence. The universe is huge, and random patterns sometimes line up by accident. The bigger the data, the more likely a strange match shows up. But the alignment is held in measurements from 3 different space missions, with better and better instruments. Each new map has made the signal harder to dismiss. Another explanation is contamination. Maybe dust in our own galaxy or light from the solar system is bleeding into the data and creating a fake pattern. Astronomers have spent years trying to clean the maps of every possible source of local noise. The alignment remains. That leaves the uncomfortable possibilities. Some physicists wonder if the universe has a hidden structure we never accounted for. Perhaps space itself is not the same in every direction. Perhaps there is a faint twist, a tilt, or a special axis built into the cosmos. If that is true, then one of the deepest principles of modern science, the idea that no place or direction in the universe is special, would be wrong. A more radical idea is that the alignment is a clue about something far larger. A few researchers have suggested that we might live inside a bigger structure, like a giant rotating region or a leftover from how the universe first inflated. The axis of evil, in that case, would be the shadow of something much grander pressing on our local sky. For now, no one knows. The pattern sits in the data, refusing to disappear, hinting that the universe might quietly know exactly where we are. And the further you push into the basics of physics, the worse it gets. Because the universe should not exist at all. At the very beginning, when the cosmos was less than a second old, something happened that defies every law of physics we know. Energy was pouring into matter. According to every experiment ever done, when energy turns into matter, it always produces two things in equal amounts: particles and antiparticles. Each one is the mirror image of the other. They have the same mass but opposite charges. When they meet, they destroy each other completely, releasing a flash of pure light. This means the early universe should have been a perfect storm of creation and destruction. For every particle of matter that appeared, an antiparticle appeared at the same moment. They should have collided, annihilated, and left behind nothing but a fading glow of radiation drifting through empty space. There should be no stars, no galaxies, no planets, no people. The universe should be an empty sea of light, and yet, here we are. Somehow, when the dust settled, matter won. The cosmos is built entirely from one side of the equation. Antiparticles are real and can be made in labs, but they are vanishingly rare in nature. Everything you can see, touch, breathe, or measure is made from regular matter. The mirror twin is gone. To get a universe like ours, the balance had to be broken in the earliest fraction of a second. For every billion antiparticles, there had to be 1,000,000,001 particles. That tiny excess survived the Great Annihilation. Everything we know is built from those leftovers. The sun, the moon, the air around you, your own body, are all made from a 1 in a billion accident at the dawn of time. The question is, why? Scientists have searched for an answer for decades. They have built enormous machines, like the Large Hadron Collider beneath the border of France and Switzerland, to smash particles together at nearly the speed of light. The hope is that one of these collisions might reveal a subtle difference between matter and antimatter, a reason why nature picked one side. They have found tiny hints. Some particles do seem to decay in slightly unequal ways, but the differences they have found are far too small. They cannot explain the lopsided universe we live in. The math still says everything should have cancelled out, so researchers keep looking. Maybe there is an unknown particle that tipped the scales, maybe a hidden force, only active in the first instance after the beginning, gave matter the edge. Maybe the laws of physics themselves were different back then, working in ways we cannot recreate. A few physicists have raised an even stranger possibility. Maybe the missing antimatter is not missing at all. Maybe it exists, far away, in a separate region of the cosmos we cannot see. A mirror universe, built from the leftovers, drifting in the dark on the other side of the beginning. If that is true, the cosmos may be split in half. Two hemispheres born together, fated never to meet, because the moment they touched, both would vanish in a final burst of light. Whatever the truth is, your existence is a riddle. The fact that anything exists at all should not have happened. And the riddle deepens, because every other rule of reality also seems carefully balanced on a knife's edge. Imagine a control panel with 24 dials. Each dial sets a different rule of physics. The strength of gravity, the mass of an electron, the energy stored inside an atom's core, the speed at which the universe expanded right after the beginning. Now imagine that almost every one of those dials is set to a precise value. Move any of them, even slightly, and the universe falls apart. Stars never form, atoms never come together, life never appears. Reality, as we know it, simply does not happen. This is not science fiction. This is what physicists actually find when they study the basic constants of nature. And it is one of the most unsettling problems in all of science. Take gravity. If gravity were just a little stronger, stars would burn through their fuel in a few million years instead of billions. There would be no time for life to evolve on any planet around them. If gravity were a little weaker, stars would never light up at all. The universe would be a cold, dark cloud of gas. The strong nuclear force, the glue that holds atomic cores together, is even more delicate. Change its strength by just a few percent, and either no atoms heavier than hydrogen can form, or every atom collapses into a dead, fused mass. Either way, no carbon, no water, no chemistry, no biology. Then there is the energy hiding in empty space. By the math of physics, this energy should be enormous. If it were anywhere near its expected value, the universe would have ripped itself apart in the first instant of its life. The fact that it sits at almost zero, but not quite, is one of the most baffling numbers in all of science. It is fine-tuned to a level that strains the meaning of the word coincidence. Scientists call this the fine-tuning problem. 3 main answers have been proposed. The first is luck. The universe is the way it is because, by sheer chance, the dials landed on the right values. The trouble is that the odds of so many constants lining up so precisely are staggeringly small. Luck alone feels like a weak explanation. The second is design. Some thinkers argue that the fine-tuning is a sign that the universe was set up on purpose, by something or someone we cannot detect. Science cannot test this idea, and most physicists set it aside, but it lingers at the edges of every conversation. The third is the most popular among scientists today. It is also the most disturbing. Maybe our universe is not the only one. Maybe there are countless universes, each with different settings on the dials. Most of them are dead, empty, or torn apart. Only the rare ones with the right values produce stars, planets, and minds capable of asking the question. In that view, we are not lucky. We are simply alive in the only kind of universe where being alive is possible. The dead ones never get an observer to notice them. The idea is called the multiverse, and it is taken seriously by some of the most respected physicists in the world. It is also impossible to prove, because we cannot see beyond our own cosmos. What we can say is that this universe is balanced on a razor's edge. And the next mystery cuts even deeper, because the very idea of time may be a trick of the mind. You feel time move. The past is behind you. The future is ahead. The present is happening right now. It feels obvious. It feels real. According to a large group of physicists, it is also wrong. In the deepest equations of physics, there is no special moment called now. There is no flow. There is no past that is finished and no future that has not yet arrived. There is only a vast, motionless structure in which every moment exists at once. The Big Bang, your birth, this exact second, the death of the sun, the heat death of the universe, all of it, sitting side by side, like every frame of a film stacked together. This idea is called the block universe, and it comes straight out of Albert Einstein's theory of relativity. Relativity proved that time is not the same for everyone. A person moving at high speed experiences time differently than someone standing still. A clock at the top of a mountain ticks slightly faster than a clock at sea level. There is no single universal now that everyone shares. What is happening now for you is not the same as what is happening now for someone on the other side of the galaxy. If now is different for everyone, then now cannot be a real thing. It must be a feature of your perception, not of the universe. Einstein himself wrote about this in a letter near the end of his life. After a close friend of his died, he tried to comfort the man's family. He wrote that the difference between past, present, and future is, for those who believe in physics, only a stubborn illusion. He meant it literally. In the block universe, your entire life already exists. The moment you first opened your eyes as a baby is still there, in its place. The last breath you will ever take is also already there, fixed in the structure of reality. You only experience them one at a time because of how your brain is built, sliding through the block like a single bead on an enormous string. To picture it, imagine a long roll of film. Every frame is real. Every frame is permanent. When you watch the film, it feels like motion. Characters move. Time passes. But the film itself is not moving. It is just sitting there. The motion is in the projector, not in the frames. Your mind, in this view, is the projector. Time is the illusion of motion as your consciousness sweeps through frames that never change. Not every physicist accepts this picture. Some argue that the present really is special, and that the future is genuinely open. They believe new moments are continuously being created, and that the past is gone for good. The debate has gone on for over 100 years, and it is far from settled. What is settled is that the human sense of time does not match the math. The equations do not know which direction is forward. They work the same whether time runs left or right. That raises an obvious question. If physics does not know the difference between past and future, why do you? Why does the universe feel like it is moving when nothing in the equation says it has to? You can remember yesterday. You cannot remember tomorrow. You can scramble an egg, but you cannot unscramble it. You can break a glass on the floor, but you cannot watch the shards leap back into your hand. Every experience you have ever had moves in one direction, from past to present to future. Forward. Here is the problem. Almost every law of physics works the same in both directions. Watch a video of two billiard balls colliding and bouncing apart. Play it forward. Play it backward. Both versions look natural. Both follow the rules of motion exactly. Nothing in the basic equations of nature says one direction is right and the other is wrong. So why does time only move one way for you? The answer hides in a single law, called the second law of thermodynamics. It is one of the most powerful rules in all of science, and one of the most quietly strange. In simple terms, it says that disorder always increases. Things fall apart, heat spreads out, order gets harder to maintain. A neat room becomes messy on its own, but a messy room never tidies itself. Scientists measure disorder with a quantity called entropy. Low entropy means order, like a fresh deck of cards in perfect sequence. High entropy means disorder, like that same deck shuffled into chaos. In every closed system, entropy always rises, never the other way around. That single rule is what gives time its direction. The past is the version of the universe where there was less disorder. The future is the version where there is more. Your memories form by adding a tiny bit of order in your brain while spreading out a little disorder in the rest of the world. That is why you can only remember the direction in which entropy was lower. You cannot remember the future, because the future has more disorder than now, and your memory only works in the other direction. Even cause and effect run on this same rule. Striking a match raises the order in the flame for an instant, but spreads heat and smoke and light into the surrounding air, raising the total disorder. Every action you take adds a little chaos to the cosmos. This means the entire feeling of time, the sensation of one moment leading to the next, comes from a slow, steady drift toward greater mess. And here is the part that haunts physicists. The early universe was, somehow, in an extraordinarily ordered state. At the moment of the Big Bang, entropy was almost zero. The cosmos was packed into a hot, smooth, low disorder beginning. Every moment since has been a long slide downhill toward more chaos, more heat spread out, more structure broken down. No one knows why the universe began in such an unusual condition. There is no clear reason in physics for it. It is sometimes called the past hypothesis, and it sits at the bottom of everything. Your sense of time, your memories, your ability to plan, all rest on a low entropy beginning that no theory has yet explained. If the universe had started in disorder instead, time, as you know, it would not exist. There would be no clear forward, no clear backward. Just a soup of randomness in every direction. The arrow of time, in the end, points from one strange beginning to one strange end. And one of the stops along the way is even stranger. A place where the rules of physics seem to break down completely. Drop a book into a fire, and the book seems to vanish. The pages curl, the cover blackens. In the end, only ash and smoke remain. It looks like the words are gone forever. In physics, they are not. In principle, if you could track every speck of ash, every molecule of smoke, and every burst of light, you could reconstruct the original book. The information was not destroyed, it was only scrambled. This idea is one of the deepest rules of nature. Information about the past is preserved. The universe never truly forgets. Then there are black holes. And black holes seem to break that rule. A black hole forms when an enormous star collapses under its own gravity. The collapse becomes so violent that nothing, not even light, can escape from its surface. From the outside, a black hole looks like a perfect drain in the fabric of space. Anything that crosses its edge, called the event horizon, is gone from the rest of the universe. For decades, physicists thought black holes were truly eternal. Once something fell in, it stayed in forever. The information about what fell in was hidden, but at least it was somewhere, locked behind the horizon. Then, in the 1970s, a young physicist named Stephen Hawking made a discovery that changed everything. He showed that black holes are not perfectly sealed. They leak. Very slowly, over unimaginably long periods of time, they release a faint glow of particles. This glow is now called Hawking radiation. As the radiation drifts away, the black hole shrinks. After a long enough time, the black hole disappears entirely. This sounds elegant, until you ask the obvious question. Where did the information go? If a black hole eats a star, a library, a planet, anything at all, and then slowly evaporates into a featureless glow of radiation, then the original details should still be hidden inside that glow somehow. The radiation should carry the fingerprints of everything that ever fell in. According to Hawking's original calculations, it does not. The radiation looked completely random. There was no sign of the star, the library, the planet, or anything else that had ever crossed the horizon. The black hole had taken a precise, detailed object and turned it into nothing but featureless heat. The information was simply gone. This became known as the black hole information paradox, and it has been called one of the deepest problems in modern physics. The math of black holes says information is destroyed. The math of everything else says information cannot be destroyed. Both cannot be right. If information really can be erased, then the universe does not have to remember the past. Cause and effect become fragile. Whole regions of reality could vanish, leaving no trace. The basic logic that science depends on starts to wobble. For 50 years, physicists have fought over this puzzle. New theories have been proposed. Some suggest the information sneaks out in subtle patterns inside the Hawking radiation, too faint to see in the original calculation. Others propose that information is stored on the very surface of the event horizon, like writing on a wall, and slowly leaks back into the universe as the black hole evaporates. Recent calculations are starting to lean toward the idea that information does survive after all. But no one is fully sure. and one of the strangest possible answers turns reality itself inside out. Look at your hand. It feels solid. It has weight. It moves in 3 directions, up and down, left and right, forward and back. The world around you behaves the same way. Rooms have height, width, and depth. Space is 3-dimensional, and time runs through it like a fourth. Some of the most respected physicists in the world believe this is an illusion. According to a powerful idea called the holographic principle, every 3-dimensional region of space, including the one you are standing in, may actually be a projection of information stored on a 2-dimensional surface far away. Reality, in this view, is something like a hologram. The depth you see is real to you, but the actual information that builds the world might be flat, painted onto a distant boundary you cannot reach. This sounds insane. The math, however, is dead serious. The idea grew out of the work on black holes. When physicists studied how much information a black hole can hold, they expected the answer to depend on its volume, the amount of space inside. Instead, the math kept giving an answer that depended only on the surface area of the event horizon. The 2-dimensional skin around the black hole, not the 3-dimensional space inside, controlled the amount of information. That should not have been possible. It was as if a library's entire collection was determined by the size of its walls, not by how many shelves it could fit inside. A handful of physicists, including Gerard 't Hooft and Leonard Susskind, took the results seriously and pushed it further. What if this was not a quirk of black holes? What if every region of space worked the same way? What if all the information that makes up your room, your body, the galaxy, was actually written on a surface somewhere? And the 3-dimensional world you experience was a kind of decoded image of that surface. In the late 1990s, a physicist named Juan Maldacena found the strongest piece of evidence yet. He showed that certain models of the universe, with gravity and 3 dimensions inside, are mathematically identical to simpler models on the 2-dimensional boundary around them. 2 completely different descriptions, one with extra space, one without, give the exact same answers. Both are equally valid. Both are equally real. His work has been tested and used by thousands of physicists since in studies of black holes, particle collisions, and the early universe. It works. What it suggests is shocking. The smooth, deep, 3-dimensional world around you may be a richer version of something flatter and simpler. The 3rd dimension, the one you take for granted, may be emergent, not fundamental. Born out of patterns on a surface, like a hologram on a credit card. It does not mean the world is fake. The chair beneath you is still there. The pain of stubbing your toe is still real. It only means that the deepest level of reality may not look like what you see. Underneath the apparent solidity of the world, there may be a coded sheet of information, and your senses may only be reading the surface. Some physicists believe this is the future of all of science, a new map of reality where space, time, and matter are all built out of something even more basic: information itself. And if information can build a universe, a question becomes impossible to dodge. What if someone is writing it? You think you are reading these words in a real world. Lights are on, air is moving, somewhere outside, traffic is passing by. It all feels solid, continuous, and obviously real. A growing number of serious scientists are no longer sure. The simulation hypothesis is the idea that the universe you experience is a computer simulation, run by some far more advanced intelligence. For decades it was treated as a science fiction toy, fun to talk about but not worth studying. That has changed. Today, leading physicists, philosophers, and engineers openly debate it in lectures, books, and journals, not because anyone has proven it. Because the more closely they look at reality, the more strangely it behaves. The clearest version of the argument was laid out by the philosopher Nick Bostrom in 2003. He pointed out 3 possibilities. First, every advanced civilization goes extinct before they build powerful enough computers to simulate worlds. Second, advanced civilizations exist, but choose not to run simulations. Third, advanced civilizations exist, run vast numbers of simulations, and most of the people in those simulations would not know they were inside one. If the first two are false, the third becomes likely. In that case, the odds that you are in the one original universe, rather than one of the countless simulated copies, become very small. That is the philosophy. The physics is what makes it uncomfortable. The universe has features that look suspiciously like the choices a careful programmer would make. The speed of light, for example, sets a hard limit on how fast information can travel. Computer simulations often have a maximum processing speed for the same reason. Inside an atom, you find a smallest possible step of energy, called a quantum. The world is not infinitely smooth. It is broken up into discrete chunks, like the pixels of a screen. When no one is looking at a quantum system, it sits in a fuzzy state of many possibilities at once. The moment something measures it, the system snaps into a single result. That looks remarkably like the way a video game only renders detail when a player looks in that direction, to save processing power. The strange behavior of particles in the double-slit experiment, the cosmic speed limit, the pixel-like graininess of energy, all of these line up with how an efficient simulation would be designed. This does not prove anything. The universe might simply happen to share features with the kinds of computers we have invented. We may be projecting our own technology onto nature. Some scientists have tried to design real tests. They look for tiny imperfections that a digital simulation might leave behind, a grid pattern in the way cosmic rays move, a subtle limit on the smoothness of space. So far, no convincing signs have been found. The universe, if it is a simulation, is very well written. A few physicists go further. They argue that even if we are inside a simulation, it changes very little in practice. The chair still holds you. The math still works. Whoever, or whatever, is running the program has built a world that obeys consistent rules. From the inside, those rules are reality. The unsettling part is not whether it is true. It is that the question has stopped being silly. And the next strange behavior of matter does not need any computer to be disturbing. In a lab, scientists fire a particle at a barrier. The barrier is too high for the particle to climb. According to the rules of everyday physics, it should bounce back. It should be stopped. There is not enough energy in the particle to push through. The particle goes through anyway, not over the wall, not around it, through it, as if the wall were not there. This effect is called quantum tunneling, and it is not a thought experiment. It happens millions of times a second, inside the chip in your phone, inside the sun, and inside your own body. The strangest thing about it is that it is real, common, and necessary for the universe to work. Here is what is happening. At the smallest scales, particles do not have fixed positions. They behave as if they are smeared out in space, a cloud of possibility that describes where they might be. When this cloud meets a barrier, most of it bounces back, but a small portion of the cloud leaks through to the other side. That leakage is the particle's chance of suddenly appearing past the barrier, as if it had been there all along. If the cloud reaches the other side, sometimes the particle does too. It does not gather extra energy. It does not break the wall. It simply ignores it. In a sense, the particle exists on both sides of the wall at once, until it is observed. Most of the time, when someone checks, it has stayed in front of the barrier. Once in a while, it is found on the other side, having crossed something that, by the older rules of physics, it should never have been able to cross. This is not a quirk. This is how the sun shines. In the core of the sun, hydrogen atoms are being squeezed together so hard that they fuse into helium, releasing huge amounts of energy. The trouble is, hydrogen nuclei push each other away with enormous electric force. By the old rules, the sun should not be hot enough to overcome that force. Fusion should be much rarer than it is, and the sun should be far dimmer. Quantum tunneling solves the problem. Hydrogen nuclei do not need to have enough energy to push through the barrier between them. They only need enough probability to leak through. Every second, an enormous number of nuclei tunnel through the wall. They should not be able to cross, fuse, and release light and heat. Without tunneling, the sun would barely glow. Without tunneling, no star in the universe would shine the way ours does. Without tunneling, life on Earth would never have begun. Tunneling is also the reason your phone, your computer, and every modern chip work at all. The transistors inside them rely on electrons hopping across thin barriers in ways that only quantum tunneling can explain. As chips have gotten smaller, engineers have had to design around the constant unwanted tunneling of electrons through walls that are now only a few atoms thick. It is happening inside you right now. Certain chemical reactions in your body, including parts of how DNA can mutate, involve particles tunneling through energy barriers. The deepest mystery is what tunneling actually means about reality. Particles are not pushing through anything. They are using a built-in rule of the cosmos that allows them to appear on the other side, with no path in between. And the question of when that appearance becomes real opens an even darker door. At the smallest scales, the universe does not deal in facts. It deals in probabilities. A particle is not in one place. It is everywhere it might be, all at once, in a haze of possibilities. The math that describes this haze is precise. It works perfectly. Every prediction has been confirmed in lab after lab for nearly 100 years. There is just one problem. None of that fits the world you experience. You never see a particle smeared into a cloud of maybe. You see a single thing, in a single place, at a single time. Somehow, between the math of the haze and the experience of the world, possibility becomes a reality. Physicists call this the measurement problem, and after a century of work, no one has fully solved it. The trouble shows up in a simple way. Imagine a tiny particle inside a sealed box. According to quantum theory, until someone checks, the particle is in many places at once. It is not hiding in one spot, waiting to be found. It is genuinely spread out, in a state of pure possibility. The moment a measurement happens, the haze collapses to a single answer. The particle appears in one place. Every other possibility instantly disappears. What counts as a measurement? That is where things break down. The math does not say. A detector in a lab triggers the collapse. So does a single atom being struck by the particle. So does a flash of light. So does an open camera. The list keeps growing, and no clear line separates measurement from ordinary interaction. Some physicists argue that any contact with the rest of the world is enough. As soon as the particle interacts with anything bigger than itself, the haze of possibilities gets tangled with so many other particles that it acts, for all practical purposes, like a single outcome. This is called decoherence, and it explains a lot of what we see. But it does not really explain why one specific outcome ends up being the one you observe, while the others fade away. Other physicists argue that the human mind is what triggers the collapse. Until a conscious observer becomes aware of the result, the universe stays in a haze. The moment a mind learns the answer, reality clicks into one shape. This idea was taken seriously by some early founders of quantum theory, including Eugene Wigner. It has fallen out of favor with most modern physicists, but it has never been disproven. It also gives an uncomfortable feeling because it places consciousness at the center of reality. A third group abandons the idea of collapse entirely. They argue that no single outcome is selected at all. Every possibility actually happens. In its own version of the universe, you only experience one because you are one of the versions of yourself. The others are real too, just not where you can reach them. The disturbing part of the measurement problem is what it says about the world around you. The haze is mathematically real. The single, solid outcomes you see are not in the equations. Somewhere between the two, reality is being chosen, and the rule that chooses it is unknown. The walls, the floor, the sky, all of it sits on top of this unanswered question. And one of the most famous answers to that question imagines countless other versions of you, all real, all alive. Inside a sealed box, scientists imagine placing a cat, a vial of poison, and a single radioactive atom. The atom has a 50-50 chance of decaying in the next hour. If it decays, a tiny detector breaks the vial. The cat dies. If it does not decay, the cat lives. By the rules of quantum theory, until someone opens the box, the atom is in a haze of both states at once, decayed and not decayed, triggered and not triggered. By extension, the cat is in a haze too, alive and dead, at the same time. This thought experiment was created by the physicist Erwin Schrödinger in 1935. He did not believe his own example. He used it to point out how absurd quantum theory sounded when you applied it to ordinary objects. A cat cannot be alive and dead at the same time. That is impossible. The trouble is, the math says it can. In the haze, every possible result of every event coexists. The only thing that picks a single outcome is the act of measurement. The question Schrödinger forced people to ask was simple. What is so special about opening the box? In the late 1950s, a young physicist named Hugh Everett offered a deeply strange answer. There is nothing special about opening the box. The collapse never actually happens. Every possibility is real. Every outcome occurs. His idea is now called the many worlds interpretation, and it is one of the most popular ways to make sense of quantum theory today. Here is how it works. When the box is opened, the universe does not pick one result, it splits. In one branch of reality, the atom decayed, the vial broke, and the cat is dead. In another branch, the atom held together, and the cat is alive. Both branches are real. Both branches continue. The only thing that happens is that you, the observer, also split. One version of you finds a dead cat. Another version, in a parallel branch, finds a living one. Each of you experiences a single outcome and assumes that is the whole story. Scale this up. Every quantum event in the cosmos, every electron that could spin up or down, every photon that could go left or right, branches the universe again. Each split is small, but the splits never stop. The result is an unimaginable tree of realities, growing in every instant with countless copies of Earth, the galaxy, and you, scattered across the branches. In some, you took the job you turned down. In others, you said something you only thought of in this one. In others, your parents never met. In others, life itself never began. All of them, if Everett was right, are equally real. You only feel like you're in one because each version of you is locked inside the branch that splits off with them. There is no way to visit the other branches. The math does not allow signals between them. Each version of reality goes its own way forever. For many physicists, the appeal is that no special collapse is needed. The math runs cleanly from start to finish. The universe is one giant, ever-branching structure, and everything that can happen does. For others, it is the price that is unbearable. Endless copies, endless deaths, endless choices. A cosmos so vast that your single life is one thread among an ocean of others. And the wildest possibility of all is the one where the future reaches back and touches the past. In a quiet laboratory, scientists run a strange version of the double-slit experiment. They fire particles at the two slits, one by one. After each particle has already passed through, they make a choice. They decide at the last possible moment whether to look at which slit it went through. The result is the same as before. If they choose to look, the particles behave like simple objects, going through one slit. If they choose not to look, the particles behave like waves, going through both. The unsettling part is the timing. The decision is made after the particle has crossed the slits. The particle has already done whatever it was going to do. And yet, its behavior depends on what the scientists choose to do next. This is the delayed choice experiment, first proposed by the physicist John Wheeler. It has been carried out many times, with light, with electrons, and with photons sent across long distances in a lab. The result holds. The future choice of the observer seems to reach back and shape what already happened. Physicists are careful with this idea. They stress that no signal travels backward in time. Nothing in the experiment lets you send a message to yesterday. The math of quantum theory does not allow it. But the experiment still suggests something deeply strange about how reality settles itself. In the standard view, a particle does not have a fixed history. Until something is measured, every possible path the particle could have taken stays alive in the math. The act of measurement does not just reveal what happened. It selects which version of the past becomes real. Some researchers go further. They argue that the future and the past might be linked in both directions. In this view, the universe is not a movie running forward from a fixed beginning. It is more like a story being written from both ends at once, with future events helping to determine which past actually happened. This idea is called retrocausality, and it sounds insane. Cause should always come before effect. Strike a match, and the flame follows. Throw a stone, and the ripple appears after. The whole logic of life depends on that order. In the equations of quantum theory, that order is not as strict as you would think. The math is symmetric in time. It treats a particle moving from past to future the same as one moving from future to past. Most physicists assume only one direction is real. A few have started asking whether both might be. Some recent experiments have tested retrocausal models. They have shown that certain quantum effects are easier to explain if you allow future measurements to influence past states, in a limited way. No information is sent backward. No one can warn their younger self. But the puzzle pieces fit more cleanly when time is not treated as a one-way street. If reality really works this way, the world you experience is the result of constant negotiation between past and future. The present moment is shaped from both sides. Every choice you make may, in a small way, help determine what came before it. You will never feel it. Your memories will keep their familiar order. But the deepest description of the cosmos may include a quiet handshake across time, with the future helping to choose its own past. And memory itself, the very thing you trust to tell you what really happened, may not be as reliable as you think. A famous cartoon bear has a fluffy tail and wears a red shirt. Or does he? Millions of people remember the bear's name as Bernstein. Books, photos, and old recordings show the name as Berenstain. People swear they remember the famous evil queen saying, "Mirror, mirror on the wall." The film, every copy of it, has always said, "Magic mirror on the wall." Crowds of grown adults remember a famous human rights leader dying in prison decades ago. He walked out of that prison alive, led a country, and lived for many years afterward. These are not isolated cases. Whole communities share the same false memory in detail with confidence. The pattern has been named after one of its most striking examples, and it is called the Mandela effect. For most psychologists, the explanation is simple. Memory is not a recording, it is a reconstruction. Every time you remember something, your brain rebuilds the scene from scattered fragments. Small details drift. Familiar patterns fill in the blanks. When many people are exposed to the same images, the same phrases, the same cultural shortcuts, their brains often make the same mistakes. A famous queen has a mirror. So, mirror, mirror sounds right. A famous cartoon family of bears feels like a familiar last name. So, Bernstein feels correct. That is the calm answer, and it is supported by decades of research on how memory really works. Eyewitnesses to crimes routinely misremember faces, clothes, even what side of the street they were standing on. Experiments have shown that people can be convinced they remember entire childhood events that never happened. The brain is excellent at telling a coherent story. It is much worse at storing exact details. Some people are not satisfied with this answer. They look at the sheer number of shared mistakes, the strength of the certainty, and the way some of the false memories feel more real than the actual facts. They ask whether something stranger could be at work. The wilder theories tie the Mandela effect to other ideas in modern physics. Some suggest that if many parallel realities exist, some people might be tuning into echoes from a slightly different branch. The mind, in that view, is a slightly leaky receiver. Faint impressions from nearby versions of the past bleed into the memory of this one. Others suggest that history itself is being rewritten in subtle ways, and that the human brain occasionally catches a glimpse of the older version before the change is complete. Scientists who study the brain reject these explanations. They point out that all the data needed to explain the Mandela effect already lives inside the way memory works. They are right that no hard evidence has ever shown a real shift between realities. The simplest answer remains that the human mind is unreliable. The reason the effect lingers in conversations about reality is what it reveals about your own grip on it. The certainty you feel about your own memories is not a guarantee of truth. Confident memories can be entirely wrong. Whole groups can be wrong in the same way. The version of the past you trust is, in part, a story your brain is telling you right now, in the present. That alone is unsettling enough. The world your mind reports may not match the world that really happened. And the world itself, even when nothing is in it, is far stranger than empty. Imagine the perfect emptiness. A sealed box with all the air sucked out. No atoms, no dust, no light passing through. According to common sense, there would be nothing inside. A pure nothing. According to physics, that box is full. At the smallest scale, the vacuum is not still. It is alive. Pairs of particles flicker into existence, exist for less than a billionth of a second, and vanish again. New ones appear in their place. The cycle never stops. Every cubic inch of empty space, even in the deepest regions between galaxies, is humming with a constant traffic of particles popping in and out of reality. These are called virtual particles, and they are real in every sense that matters. The basic idea comes from a rule in quantum theory called the uncertainty principle. It says that nature has a limit on how much you can pin down at the same time. The more precisely you know one property of a tiny system, the less precisely you can know the other. In the case of energy and time, this means the universe is allowed to borrow a small amount of energy, as long as it gives it back quickly. The bigger the loan, the shorter the time. Empty space takes advantage of this rule constantly. Energy flickers into matter in the form of paired particles, lives for an instant, and then disappears. The universe pays itself back before anyone can notice. Nothing about this violates the conservation of energy. It is a kind of cosmic bookkeeping trick. The effects of this hidden activity are everywhere. Electrons inside atoms feel a tiny extra wobble because of virtual particles flickering around them. This wobble has been measured to an extraordinary precision, and the predictions of quantum theory match the experiments to many decimal places. It is one of the most accurate agreements between math and reality in the history of science. The cores of atoms are held together by particles that, in part, work as a swarm of virtual exchanges. Magnets push and pull on each other through clouds of virtual photons whisking back and forth. Even the weight of certain particles depends on their interactions with the boiling vacuum around them. There is a more dramatic example. In the late 1940s, the physicist Hendrik Casimir predicted that two flat metal plates, placed extremely close together in a perfect vacuum, should be pushed together by an invisible force. The reason is that the gap between them is too small to allow some of the virtual particles to fit, while the outside vacuum has no such limit. The unequal pressure of the virtual storm pushes the plates inward. The effect is tiny but real, and it has been measured in labs with extreme care. This means the vacuum has measurable, physical pressure. Empty space is pushing on objects. Empty space contains energy. By some estimates, the energy stored in any region of empty space, if you could harvest even a fraction of it, would dwarf anything we have ever produced. No one has ever found a way to extract it usefully. The energy hides inside the rules that make the universe stable, Try to pull it out, and the math closes the door. It also raises a darker problem. When physicists try to predict how much energy should be hiding in empty space, the answer they get is wildly larger than what the universe actually contains. By a margin that may be the worst prediction in the history of science. The vacuum, in other words, is full of secrets we cannot read. And one of those secrets has already been caught in the act, pressing on metal plates with a force that should not exist. In a quiet lab, 2 thin metal plates hang inside a sealed vacuum chamber. The air has been pumped out. The temperature is held steady. The plates are positioned so close to each other that the gap between them is smaller than a human hair, by an enormous factor. Then the scientists let go. The plates move on their own. They drift toward each other slowly but steadily, as if pulled by an invisible hand. Nothing is between them. Nothing is touching them. The space around them is as empty as physics can make it. This is the Casimir effect, and it is one of the strangest confirmed predictions in modern physics. It is also one of the clearest pieces of evidence that empty space is not really empty. The man who predicted it, Hendrik Casimir, was studying the strange behavior of the vacuum. He realized that if empty space is filled with countless virtual particles flickering in and out of existence, those particles must have wavelengths, the same way any wave does. Outside the plates, all kinds of wavelengths fit in the gap. Inside the gap between 2 very close plates, only certain wavelengths can fit. The smaller the gap, the more wavelengths are excluded. That mismatch creates a tiny pressure difference. The vacuum outside pushes harder than the vacuum between the plates. The result is a gentle force squeezing the plates together. The closer they get, the stronger the force becomes. When Casimir worked this out in 1948, no one had any way to test it. The effect is so small that any tiny vibration, electrical charge, or stray particle ruins the measurement. For decades, it stayed a theoretical curiosity, mentioned in textbooks but never confirmed. Then, in the late 1990s, physicists finally built setups precise enough to see it. They used carefully smoothed plates, ultra-clean vacuums, and a detector sensitive enough to feel forces a fraction of a billionth of a gram in size. The plates moved. The force matched Casimir's prediction. The vacuum had pushed. Since then, the effect has been measured in many forms, with curved surfaces, with different materials, even, in some setups, with measurable effects on tiny mechanical parts. Engineers building extremely small devices have to take it into account, because at the right scale, the pressure of nothing is large enough to stick parts together or change how they move. The Casimir effect proves something simple and shocking. The vacuum has structure, it can exert force, it can transfer energy. The empty space between objects is, in a real sense, alive with hidden activity, and that activity does work in the world. In some experiments, scientists have even seen a version of the effect where moving mirrors in a vacuum produce light, generated from the virtual storm itself. Real photons pulled out of nothing, simply by shaking the boundaries fast enough. This has been called the dynamical Casimir effect, and it has been observed in carefully built systems. The deeper meaning is hard to digest. The space you walk through every day is humming. It is pressing softly on the walls. It is filled with potential energy that no one knows how to use. The universe, even in its most apparently empty places, is restless. And one of its biggest hidden problems is not what fills empty space, but what holds your body and the entire planet down to the ground. Stand up. Walk across the room. Drop your phone, watch it fall, and pick it back up. Gravity, the force you feel every second of your life, is the most familiar thing in the universe. It is also, secretly, the most broken. Modern physics is built on 2 great pillars. One is general relativity, Einstein's theory of gravity. It describes how massive objects bend space and time around themselves, and it explains the motion of planets, stars, galaxies, and the universe as a whole. The other is quantum mechanics. the theory of the very small. It governs particles, atoms, light, and the subatomic forces that hold matter together. Both theories are spectacularly successful. Both have been tested to extraordinary precision. Both work. They cannot both be right. When physicists try to combine them, the math breaks. The equations explode. Infinities pour out where finite answers should be. Try to ask what happens to gravity inside an atom. The theory fails. Try to ask what happens at the very center of a black hole, where matter is crushed to a point. The math gives up. Try to ask what the universe was like in the first instant after the Big Bang, when everything was packed into a region smaller than an atom. Once again, no clean answer exists. Gravity is the misfit. The other three known forces of nature, the strong force, the weak force, and the electromagnetic force, all have clean quantum descriptions. Each is carried by particles, and the math works at every scale, from the cosmic to the subatomic. Gravity has nothing like that. The best quantum theory of gravity is still missing. After more than 100 years of effort, the world's most brilliant physicists have not been able to write it down. This is not a small loophole. It is a hole at the bottom of the entire structure of modern science. Below a certain size, called the Planck length, our two great theories simply have nothing reliable to say about what reality is doing. Whatever sits at the deepest level of the universe, beneath atoms, beneath the smallest waves of light, is hidden in equations that no one has been able to read. Many attempts have been made. String theory replaces the basic building blocks of matter with tiny vibrating strings, and it offers one possible way to weave gravity into the quantum world. It is beautiful, but unproven. Loop quantum gravity tries to chop space itself into tiny pieces, woven into a kind of fabric. It has promise, but it is also still incomplete. Other ideas, with names like causal dynamical triangulations and asymptotic safety, exist in research papers but have not made any verified prediction yet. Meanwhile, in the everyday world, gravity behaves itself perfectly. Apples fall, satellites orbit, light bends around the sun exactly as relativity predicts. Black holes warp space the way the equations say they should. The mismatch between gravity and quantum theory only shows up in extreme places. At the heart of black holes, at the beginning of the universe, at the smallest possible scales, where reality may not even resemble what your senses suggest. That tiny mismatch keeps every theoretical physicist in the world awake. Somewhere in those broken equations, the real story of how reality is put together is hiding. And gravity has one more secret. Its strength compared to the other forces is so absurd that physicists openly call it a problem. Hold a paperclip near a small magnet. The magnet picks it up easily. A tiny piece of metal, no bigger than your fingernail, just overcame the gravity of the entire planet. The whole Earth, with all its mass, is pulling down on that paperclip. A magnet you can fit in your palm wins. This is not just a fun trick. It is a hint that something is very wrong with how the forces of nature compare. Physicists know of 4 fundamental forces. 2 of them only show up inside the cores of atoms. They are the strong nuclear force, which holds atomic nuclei together, and the weak nuclear force, which causes certain kinds of radioactive decay. The third is electromagnetism, the force behind light, magnets, and electricity. The fourth is gravity. When scientists line up these forces and compare their strengths, they expect them to be in a similar range. Different, yes. Slightly stronger or weaker, sure. Instead, 3 of the 4 forces sit close together, with gravity floating somewhere far below. Not just a bit weaker, vastly, astronomically weaker. By the numbers, gravity is roughly 1,000,000 billion times weaker than the electromagnetic force between 2 protons. That is a 1 followed by an extraordinary number of zeros, all of them representing how easily gravity is beaten by the other forces. This is called the hierarchy problem, and no one knows why it exists. To see how strange it is, Picture a tug of war. On one side, the entire mass of the Earth. On the other side, a small magnet. Yet the magnet still pulls the paperclip up. Gravity has more participants by an incredible margin and still loses. If the other forces were even slightly weaker, the world would look completely different. Atoms would behave differently. Stars would burn differently. Chemistry, life, and matter as you know it depend on this strange imbalance. So why is gravity so faint? The truth is, no theory has produced a satisfying answer. Several ideas have been proposed. One idea, called supersymmetry, suggested that every known particle had a hidden heavier partner. The presence of these partners in the math would help balance the forces and make gravity's weakness less mysterious. Despite decades of searching, particle accelerators have not found any of these partners. The simplest versions of the theory are now in serious trouble. Another idea is even bolder. Some physicists suggest that gravity is not really weaker than the other forces at all. It only looks weaker because it is leaking into hidden dimensions of space. In this view, the universe has more than the familiar 3 dimensions of width, height, and depth. Extra dimensions are folded up so tightly that you cannot see them. The other forces are stuck in the 3 normal dimensions. Gravity alone slips between all of them. By the time it gets to you, only a tiny fraction of its real strength is felt. If this is true, then gravity is actually as strong as the other forces, somewhere out of sight. The shortfall is an illusion caused by space itself hiding part of the picture. So far, no experiment has caught gravity escaping into hidden dimensions. The hierarchy problem remains open. The world you live in is shaped by it. Stars exist as they do because gravity is weak enough to lose to electromagnetism inside them. Planets exist because gravity is just strong enough to clump matter together without crushing it. Your body is built from atoms held together by electric forces that overwhelm gravity by an absurd margin. A different reality, with even slightly different ratios, would have no you in it. And those hidden dimensions, if they are real, might be the doorway to a much wilder picture of the universe. You move through 3 dimensions every day, forward and back, left and right, up and down. Time the 4th runs through all of them. Physicists have spent decades exploring the possibility that there are more, many more, maybe 6, maybe 7, maybe more than 10 in total. All of them invisible. This is one of the central claims of string theory, the leading attempt to unite gravity with the rest of physics. The basic idea of string theory is simple in spirit, complex in detail. The smallest pieces of matter, like electrons and quarks, are not really points. They are tiny vibrating strings of energy. Each string can vibrate in different ways. The particular pattern of vibration determines what kind of particle the string acts like. One vibration, an electron. Another, a quark. Another, a particle of light. Reality, in this view, is a symphony played on incredibly small instruments. For the math of string theory to work, those strings cannot vibrate in only 3 dimensions. They need more. Different versions of string theory call for 10, 11, or even more dimensions in total. Yet you obviously do not see them. The proposed answer is that the extra dimensions are curled up, folded so tightly that you would never notice them in your daily life. To picture it, think of a long garden hose seen from far away. It looks like a one-dimensional line. Walk up close and you can see that the hose actually has a second dimension wrapped around it, the circle of its surface. A tiny ant on the hose could crawl forward or wind around the surface. The second dimension is real, but only visible at small scales. String theorists imagine the same trick happening at the smallest scales of space. At every point in your room, there may be entire little universes of extra dimensions, coiled into shapes so small they are far below anything any microscope can ever see. You move through them constantly, without ever realizing it. The shapes themselves are not random. The math allows for a vast variety of possible foldings, with names like Calabi-Yau manifolds. Each different folding gives rise to a different set of physical laws. Different masses for particles, different strengths for forces, different versions of reality. This is where string theory becomes more than a curiosity. It suggests that our universe is one of an enormous landscape of possible universes, each defined by how its extra dimensions are wrapped. The dials of physics, the fine-tuned values we saw earlier, would simply be the local settings here, picked from a much larger menu of options elsewhere. Critics push back hard. After many years of work, string theory still has not made a single confirmed prediction that other theories cannot match. Particle accelerators have not seen direct evidence of the extra dimensions. Some physicists have started to question whether string theory will ever be testable in any meaningful way. Supporters argue that the mathematics is too rich and too consistent to be wrong. String theory has already produced new tools that have been used in other fields, including black hole research and the holographic ideas from earlier chapters. Even if no one has caught a string on a detector, the framework has reshaped how physicists think about space, time, and matter. Whether or not string theory turns out to be the final answer, the basic question it raises will not go away. The world may have more rooms than you ever knew you were living in. And at the smallest possible scale, even space itself may stop being smooth. Zoom in on a photo on a screen, far enough, and you will see the picture break apart into squares of color. Each square is a pixel, the smallest unit the image is made of. Below that scale, there is no more picture. There is only the underlying grid. Some physicists believe the universe itself works this way, that the smooth, continuous world around you is only continuous at the scales you can see. Go small enough, and reality is built out of tiny units, pixels of space and time. The size of these possible pixels is set by a number called the Planck length. It is roughly 100 million trillion times smaller than a single proton, which is already too small to picture in any everyday way. To give a sense of the gap, the Planck length is to a single proton roughly as a proton is to the size of a solar system. It is the smallest distance that has any clear meaning in modern physics. Below it, the equations stop making sense. You cannot even talk about position. The concepts of here and there lose their meaning. There is a matching limit in time called the Planck time. It is roughly the time it would take light to cross one Planck length. Below this, the idea of earlier and later also breaks down. Time becomes a meaningless coordinate. What does this mean for reality? One interpretation is that these limits are simply gaps in our current theories. Physicists may eventually find a more complete description of nature that allows them to talk about smaller scales. The Planck length, in this view, is the point where current theories give up, not where reality itself does. Another interpretation is more radical. The Planck length may be a real physical limit. Space and time may not be smooth at all. They may be discrete, broken up into tiny units, like the smallest possible Lego bricks of existence. What you experience as a smooth, continuous world is the average of countless tiny steps. The same way a video on a screen looks smooth even though it is made of separate frames. Some approaches to quantum gravity, like loop quantum gravity, build this idea directly into their math. They treat space as a kind of woven fabric, made of small loops and nodes that join together to form the appearance of smooth volume. Areas and volumes do not come in any value you like. They come in discrete sizes, like cards in a deck. If reality is pixelated, the consequences are strange. There would be a smallest possible distance, a smallest possible duration, and perhaps a smallest possible piece of any quantity. Speed would no longer be infinitely fine. Trajectories might really be sequences of tiny jumps, only looking smooth from far away. Some thinkers have even tied this to the simulation idea, pointing out that any computer simulation would have to break reality into similar discrete units. Tests are underway. Several experiments are looking for any sign that light or other signals behave differently as they travel huge distances, possibly picking up tiny effects from the underlying grid of space. Photons from faraway cosmic explosions might arrive with subtle delays. Some teams have looked for grain-like patterns in the data of high-precision detectors. So far, no clear sign of pixelation has been found. The universe still looks smooth at every scale we can probe. That does not mean it is smooth all the way down. It only means that if pixels exist, they are smaller than anything we have built so far. And one of the strangest experiments in physics already lets us choose what happened after the fact. Imagine a beam of light split into two paths. Each photon, the tiny particle of light, gets to take both paths at once, the way only quantum objects can. The two paths run side by side, then come back together. The photon arrives at a detector. The arrangement is set up so that if no one looks at which path the photon took, an interference pattern appears. The photon clearly went both ways. Now add a twist. The detectors that could check which path the photon took are turned on or off after the photon has already started its journey. Sometimes they are switched on so late that, in any classical sense, the photon should already be near the end of its trip. The bizarre result is the same as before. Whenever the path detectors are switched on, the interference pattern vanishes, even if the switch happens long after the photon entered the setup. The photon decides how to behave based on what is going to happen, not just on what already has. This is John Wheeler's delayed choice experiment, taken further than the original double-slit version. It has been carried out in many forms, including a version using photons sent from a distant astronomical source. In that version, the choice of whether to measure the path is made on Earth, while the photon has been traveling for billions of years. The result is the same. Physicists are careful with their words here. The photon does not literally travel back in time. The light has clearly already crossed the distance. The deeper claim is that the question of which path the photon took is not really settled until the measurement is made. Before that, the universe holds a kind of open possibility about the photon's history. The measurement at the end of the trip selects which version of the journey ends up being the real one. It sounds like nonsense, but it is one of the cleanest experiments in modern physics. The math of quantum theory predicted it. The lab results confirm it. Different setups, different materials, different lengths of travel, all show the same thing. The story of a particle is not fixed until something forces it to be. Wheeler took this seriously enough to argue that the universe might not have a fully decided past at all. He called this idea participatory reality. In his view, observations made now might play a role in determining what the early universe looked like. Light reaching us from billions of years ago might, in some sense, only be fully real once someone here measures it. Most physicists do not go quite that far. They prefer to say that quantum systems simply do not have classical histories until interaction with the larger world fixes them. From inside the experiment, it looks like the present is reaching into the past. From outside the equations, it looks like the past was always a haze of possibilities, waiting to be settled. Either way, the everyday feeling of a fixed, finished history is challenged. The photon's path was not written in stone when it left. Bigger structures, made of huge numbers of particles, do not show these effects in obvious ways, but at the smaller scales, the story is genuinely open. The universe, deep down, may be writing itself one measurement at a time, and the question of who is doing the writing and who is doing the watching leads to an even darker possibility about your own existence. Take a strong cup of coffee. Spill it across a clean table. The drops scatter in a messy splash. Now ask yourself, could that pattern of drops, by sheer luck, ever form a perfect portrait of your face? In any single splash, no. Across an unimaginable amount of time, with random splashes happening over and over, yes. Eventually, given enough rolls of the dice, even the rarest pattern will appear. Now scale that idea up to the entire universe. Physicists know that the cosmos is full of random microscopic motion. Atoms jiggle, particles flicker, the vacuum hums with activity. Combine many particles in a closed system, give it enough time, and the laws of probability say that any possible arrangement of those particles will eventually occur, at least once, just by chance. Even very unlikely arrangements get their turn, given enough cosmic rolls of the dice. In the far future, the universe is expected to become extremely cold and empty. The stars will burn out. The galaxies will drift far apart. The black holes will slowly evaporate. What is left will be a vast, almost featureless sea of low-energy radiation. In this state, nothing interesting seems to happen. The whole cosmos becomes a quiet bath of leftover particles. Almost. Random fluctuations never stop. Even in this near-empty future, particles will keep popping in and out of existence. Most of the time, they form nothing important. Once in a very long while, by sheer chance, they form something complicated. Maybe a small clump of gas, maybe a working hand, maybe an entire brain, complete with memories, perceptions, and a sense of being alive. This kind of accidental, fully formed mind has a name. It is called a Boltzmann brain, named after the physicist Ludwig Boltzmann, whose ideas about disorder first led to this strange possibility. A Boltzmann brain would exist for only a brief flash. It would form in the random churn of particles, complete with false memories of a life that never happened, and dissolve almost as soon as it appeared. To itself, in that brief moment, it would seem perfectly normal. It would believe it had a past, a body, a world around it. None of that would be real. Only the brain's internal pattern would exist, glued together by chance. In an infinite future with infinite time, the math suggests that countless Boltzmann brains could form, possibly far more than the number of ordinary brains ever born inside stars and planets, in the normal way. That leads to an unsettling question. If random brains in deep cosmic emptiness are more common than evolved brains on planets, what makes you so sure you're not one of them? You feel like you live in a real, large, structured universe. So would a Boltzmann brain, just before it dissolved. From the inside, the experience would feel identical. Most physicists do not want to take this scenario seriously as a description of you. They use it instead as a warning sign. Any theory of the universe that predicts more random Boltzmann brains than ordinary observers is considered broken. Models that lead to this result are usually adjusted, refined, or thrown out because they cannot be matched with the world you appear to live in. That alone is a strange situation to be in. Modern physics is forced to filter out scenarios where most yous are flickering brains in dead space, simply because such a picture would make almost every memory you have a meaningless coincidence. The fact that this idea has to be considered at all says something quiet and uncomfortable about how shaky our grip on reality really is. And as if that were not enough, the most carefully measured particles in the lab are starting to disagree with themselves. Few objects in the universe seem more basic than the proton. It sits at the center of every atom. It is the building block of hydrogen, the most abundant element. It is one of the most studied particles in all of science. After decades of careful measurement, physicists thought they knew its size. Then a different kind of experiment measured it and got a different answer. A noticeably smaller proton. Same particle, different size, no one knew why. The story began with a clever idea. Physicists wanted a more accurate way to measure the radius of the proton. Normally, this is done by either firing electrons at hydrogen atoms and watching how they scatter, or by carefully studying the patterns of light given off by hydrogen as its electrons jump between energy levels. Both methods, for decades, agreed on a particular value for how big a proton really is. A team of researchers had a new approach. They built atoms in which the electron, the usual partner of a proton in hydrogen, was replaced by a heavier cousin called a muon. A muon behaves very much like an electron, except that it is far heavier. Because of that extra mass, a muon orbits much closer to the proton than an electron does. That close approach makes the system extremely sensitive to the proton's size. Small differences in the proton's radius show up as detectable shifts in the light the muonic hydrogen emits. When the team carried out the measurement in 2010, they expected to refine the existing value. Instead, their answer came back about 4% smaller than the standard value. That sounds tiny, In particle physics, it is enormous. The new result disagreed with the old one by far more than the official margins of error allowed. Either the standard measurements were wrong, or the new measurement was wrong, or something deeper was going on. This became known as the proton radius puzzle. For years, scientists hunted for explanations. They redid the older measurements with better equipment. They tested whether moons might interact with protons through some new, unknown force. They double-checked every calculation. The puzzle stubbornly refused to fade. More recent measurements have shifted closer to the smaller value. Some experiments using ordinary electrons now agree with the smaller radius, while others still side with the original larger one. The picture is not fully resolved. The proton might be smaller than physicists thought. Many of the old measurements might have had hidden errors, or some unexpected physics might be subtly affecting how muons and electrons interact with the same proton. Even if the answer ends up being a simple measurement issue, the puzzle reveals something important. The cleanest, most basic particle in nature has been giving inconsistent answers about its own size, depending on how you ask the question. The problem is not in some exotic black hole on the other side of the universe. It is in a particle you carry around with you, in every atom of your body, every second of your life. This is the sort of small, quiet anomaly that can change everything. The discoveries that have rewritten physics in the past, like dark energy or the strange behavior of light at high speeds, often started as tiny mismatches between expected and measured values. The proton radius puzzle may eventually be explained away. It may also be a crack through which a new layer of physics walks into view. And in another quiet experiment, a different particle has been wobbling in a way that no current theory can explain. In a vast metal ring, scientists let particles called muons race in circles at nearly the speed of light. The ring is built deep inside a national lab, with magnets so powerful and precise that the entire experiment is one of the most carefully controlled things ever assembled. The team is watching for one specific thing: a wobble. The muon, the same heavy cousin of the electron from the proton-sized puzzle, behaves a bit like a tiny spinning top. Inside the magnetic ring, it wobbles around as it moves. The exact rate of that wobble depends on the muon's internal magnetic properties, which in turn depend on every known force that can pull or push on it. Every known force is already accounted for. Physicists have built incredibly detailed predictions of how fast the muon should wobble, using the so-called Standard Model, the best theory of particles ever assembled. The prediction is precise to many decimal places. When the muon is measured, it wobbles a tiny bit faster than predicted. The difference is small, but in physics, at this level of precision, a small disagreement is a giant problem. The wobble measurement is one of the most accurate experiments ever performed. The prediction it is compared to is also one of the most accurate ever calculated. They should match almost perfectly. They do not. The result is sometimes called the muon G-2 measurement, because it concerns a number that physicists label G and how it differs from the value of 2. The deviation has now been seen by 2 different generations of experiments, at 2 different labs, separated by decades. The signal has not gone away. If anything, it has grown stronger as more data has been collected. This matters because if the muon really is wobbling faster than the Standard Model predicts, then there is something else pulling on it. Some force, particle, or field that has never been seen, gently tugging at the muon while it spins. The Standard Model would be incomplete. The deepest map of nature would be missing an entry. There are still doubts. Different ways of calculating the prediction have given slightly different answers. Some calculations, based on different methods of estimating tricky parts of the math, come closer to the experimental result. Others stay far away. Physicists are working on better calculations and better measurements to find out whether the discrepancy is real or an artifact of how the prediction is built. If the discrepancy survives, it could point to new physics. Possible explanations include a never-seen particle in the soup of virtual particles around the muon, or a new force that affects muons more strongly than other particles. Either would be a discovery on the level of finding a missing piece of the engine of a reality. For now, the muon refuses to settle the question. Its wobble sits stubbornly off by a small but persistent amount, and the world's best theorists are arguing about what it means. This is how the deepest revolutions in physics usually begin. Not with sudden, obvious shocks, with small, persistent disagreements between theory and measurement, with particles that fail to follow the script, with numbers that almost match but never quite do. The muon may be saying something that the universe has been hiding for a long time. We just have not yet learned how to read it. And out in the deepest reaches of space, other signals are arriving that no one can explain. In 2007, a graduate student named David Narkovich was looking through old data from a radio telescope in Australia. He noticed something odd. A brief, brilliant flash of radio waves, only a few thousandths of a second long, recorded years earlier from a region of the sky far outside our galaxy. The signal was so strong and so short that at first the team did not believe it. They checked for malfunctions. They scrubbed for interference. They cross-referenced with other instruments. Whatever it was real. It had traveled across an enormous distance, possibly billions of light years, and had ended its journey in a single fraction of a second. That single flash is now called the Lorimer burst, after the senior scientist on the team. It was the first of a strange new family of signals known as fast radio bursts. In the years since, hundreds more have been detected. New telescopes, especially in Canada and Australia, have caught fast radio bursts pouring in from all over the sky. Each one is a brief, powerful blast of radio waves. In a single thousandth of a second, a fast radio burst can release as much energy as the sun produces in days. Some come from galaxies so distant that the light has been traveling almost as long as the universe itself. Some bursts are one-off events. They flash once and never repeat. Others have been seen flashing again from the same point in the sky, sometimes following patterns that researchers can predict with rough accuracy. The question, of course, is what they are. The leading suspects involve extreme objects in space. The strongest candidate so far is a kind of star called a magnetar. A magnetar is a small, dead star with a magnetic field so powerful it is millions of times stronger than anything ever built on Earth. When a magnetar twitches or quakes, it can release titanic bursts of energy. In 2020, a magnetar inside our own galaxy was caught producing a fast radio burst, with much weaker brightness than the deep space ones, but with a similar fingerprint. That detection was a major step forward. Magnetars are clearly responsible for at least some of the signals. The story's not finished. Not every fast radio burst fits the magnetar picture. Some come from galaxies where magnetars are unexpected. Some have unusual repeat patterns. A few have been detected in regions that look quiet and empty, where no obvious source has been found. Astronomers have proposed other ideas: collisions between dense remains of dead stars, bursts from the edges of black holes, even, in the most extreme suggestions, signals from advanced civilizations. The data does not support any single answer to all cases. The category likely contains several different kinds of events, all producing brief, bright radio flashes for different reasons. For now, fast radio bursts are an open mystery. New observatories are coming online that can spot many more of them each year. Each new burst adds a tiny piece to the puzzle. Each one is a reminder that the universe is full of phenomena we do not understand, capable of releasing huge amounts of energy in fractions of a second. The deeper meaning is humbling. A flash that took billions of years to reach a small dish on Earth. A pattern that lasted less than the time it takes to blink. Energy on a scale that makes entire planets feel small. The cosmos is sending messages all the time. Most of them we still cannot translate. And one signal, long before fast radio bursts, was so strange that one of its discoverers could not stop himself from scribbling a word next to it. On August 15th, 1977, a radio telescope at Ohio State University was scanning the sky as part of a search for signals from intelligent life. The telescope, called Big Ear, automatically recorded numbers and letters that described the strength of any signal it picked up. Most of the time, the printout showed quiet noise, faint background readings, nothing unusual. A few days later, an astronomer named Jerry Eman sat down to look through the data. As his eyes ran down the columns of weak signals, he stopped. One row jumped out at him. A burst of activity so much stronger than the background that it looked like a different kind of event entirely. He grabbed a red pen, circled the sequence of characters, and wrote a single word next to it. Wow. The signal has been called the WOW signal ever since. It came from the direction of the constellation Sagittarius, far from our solar system, in a band of radio frequencies that scientists had long considered a likely choice for any interstellar broadcast. The frequency was close to the natural emission of hydrogen, the most common element in the universe. The signal lasted for about 72 seconds, the exact length of time that the telescope could remain pointed at any one patch of sky. Then it was gone. In the decades since, dozens of attempts have been made to detect it again. Big Ear itself looked back at the same spot for years. Other observatories around the world have aimed their dishes at the same region. No matching signal has ever been recorded. Whatever made the burst either turned itself off, drifted out of the line of sight, or was never going to repeat in the first place. Possible natural explanations have been suggested over the years. Some researchers have proposed that comets passing through the area could have emitted the signal, though that idea has been seriously challenged. Others have suggested rare astronomical events, glitches in the equipment, or reflected human signals, none of which have fully matched all the details. The WOW signal stands out because it appears in only one detector channel, at the right frequency, with the expected pattern of a true sky source. It fits what scientists would expect a real, distant transmission to look like. What it does not fit is anything we can clearly identify. There are other strange one-off signals in the history of astronomy. Some pulsars were first mistaken for possible alien broadcasts before scientists understood what they were. A few signals over the years have been temporarily classified as unexplained before later being traced to ordinary sources, like satellites or microwave ovens in nearby buildings. The WOW signal has survived all such explanations for nearly half a century. That alone places it in a special category. A real signal from the sky with the right shape, of the right strength, in the right frequency, that has never been recorded again. Either nature produced something briefly and uniquely strange in that direction, or someone, or something, sent one short message and went silent. Most astronomers are careful not to leap to conclusions. The WOW signal is officially listed as unexplained, not as evidence of extraterrestrial contact. The honest scientific answer is that we simply do not know. The unsettling part is what that admission implies. The universe is large enough and old enough that signals could be reaching us from anywhere. From dead stars, from violent black holes, from rare and brief astronomical events, and possibly, in principle, from other minds. So far, the sky has only said wow once. And as we keep listening, a deeper worry has begun to creep into physics itself. For most of the modern age, physics has marched forward. Each generation has found bigger telescopes, more powerful accelerators, more detailed maps of the cosmos. Each generation has answered some questions and opened others. The pace has felt endless. The territory seemed limitless. In recent years, a quiet anxiety has begun to grow in parts of the physics community. The question is no longer simply how much more can be learned. The question is whether some of what we want to know may be permanently out of reach. The most obvious limit lives in the cosmos itself. The observable universe is finite. Light has only had so much time to travel since the beginning. Past a certain distance, there is no possible signal that has yet reached us, and there never will be. because space between us and those regions is stretching faster than light can cross it. Whole sections of the cosmos are forever cut off. Whatever happens there, we cannot see. As the universe keeps expanding, this hidden region only grows. Galaxies that are now visible at the edge of our reach are slowly being carried out of sight. In the very far future, the night sky for any observer in our position will look much emptier than it does now. Most galaxies will have drifted beyond the cosmic horizon. Future astronomers, with no record of older observations, would be unable to tell that the universe was even expanding. They would believe they live in a small island of stars, surrounded by black. That is one kind of limit. There are others. At the smaller scale, the Planck length and Planck time set a wall against direct probing. Below those scales, current physics fails. Building a machine that could see directly at those depths would require energies far beyond anything humanity has ever imagined, possibly more than any civilization could ever produce without collapsing into a black hole. The smallest structure of space itself may be permanently below the level any experiment can reach. Theory also faces limits. Many of the leading ideas about the deeper structure of reality, including string theory and the multiverse, predict differences only at scales no experiment can test. We can write the math. We cannot check it directly. Some physicists worry that whole branches of theoretical physics are drifting toward unfalsifiable territory, where ideas can stay alive forever because no measurement can ever rule them out. There is also the limit of the mind. Human beings did not evolve to picture extra dimensions, time as a frozen block, or particles spread across multiple possibilities. The math demands these pictures, the brain struggles to hold them. There may be aspects of reality that are simply not built for any intelligence, shaped by walking around a savanna and counting fruit on a tree. None of this means the search has to stop. New techniques, new instruments, and new ideas have surprised the world before. The discovery of dark matter and dark energy, the mapping of the cosmic glow, the capture of gravitational waves passing through the Earth. Each was once thought to be beyond reach. Each is now part of standard astronomy. It does mean, though, that the era of confident certainty may be ending. Physicists are increasingly aware that the picture of the universe may always be partial. There will always be regions we cannot see, scales we cannot reach, possibilities we cannot decide between. The deepest answers may sit just past the edge of what evidence can ever say. And the final possibility, the most uncomfortable one, may close the circle of every chapter that has come before. You have crossed 32 chapters of strangeness. Particles that watch back. Galaxies held together by invisible matter. A universe that expands at two different speeds. A vacuum that pushes. A past that is not quite settled. A future that may already exist. Behind every one of these mysteries, one thing has stayed constant. You, the observer, the mind reading along. The most uncomfortable question in modern physics is whether that mind is, in some way, part of the picture. Most physicists prefer to keep consciousness out of their equations. The standard view is that reality runs on its own, with or without anyone to notice. Stars existed long before brains. Atoms followed the same rules in the early universe as they do today. The role of the observer is just to record what happens, not to shape it. Quantum theory keeps poking holes in this view. Whenever a quantum system is left alone, it spreads into a haze of possibilities. Whenever a measurement is made, that haze collapses into a single outcome. The equations describe both stages clearly. They do not explain the leap between them. Something turns the haze into a definite event. The simplest description of that something is an observation. For a long time, most physicists assumed that observation meant any interaction with a larger system. A measurement device, a pile of atoms, a flash of light, no mind required. This view is supported by the success of decoherence theory, which shows how quantum systems quickly lose their fuzzy behavior when they get tangled up with their environment. There is a stubborn minority of thinkers who are not satisfied. They notice that decoherence explains why we never see large objects in obvious quantum hazes, but it does not explain why a particular outcome ends up being the one any specific observer experiences. Why this version and not that one? Why your branch of reality and not another? Not a few physicists, including some of the founders of quantum theory, suggested that consciousness might be what finally fixes one outcome as real. Eugene Wigner once proposed that the mind plays a role in collapsing the wave of possibility into a single answer. The idea is controversial. Most modern physicists do not accept it. It has never been disproven. Other thinkers have gone even further. Some have argued that consciousness may be a fundamental feature of reality, woven into matter at every level. In this view, even simple physical systems carry a faint trace of inner experience, and human minds are just unusually rich combinations of those traces. This idea, sometimes called panpsychism, is taken seriously by a small but growing group of philosophers, and even some physicists. It is far from proven. It is also far from gone. The questions that connect mind and matter remain wide open. Where does subjective experience come from? Why is there any felt sense of being you, rather than nothing at all? Why does the universe contain creatures who can ask such a question in the first place? Neither neuroscience nor physics has a complete answer yet. What is striking is that the deepest puzzles of physics keep brushing up against the deepest puzzles of mind. The measurement problem, the observer in quantum experiments, the fine-tuning of constants that allow life, the strange role of information at the heart of black holes. None of this proves that consciousness creates the world. It does suggest that the line between observer and observed may be thinner than the textbooks usually admit. In the end, the universe you have explored across these chapters is a place where particles know when they are watched, where time may be an illusion, where empty space presses on metal, where galaxies sit on invisible scaffolding, and where the cosmos is expanding into a future no one can fully describe. Standing in the middle of all of it is you. A small, brief, conscious thing, looking out at a reality that refuses to behave. Something about reality is wrong. The strangest part of all is that you are the one noticing.